Recall that the reason why we came up with this definition of linear dependence and independence is because we were trying to capture a phenomenon of a vector being redundant in a spanning set. So being able to remove a vector from a spanning set and still end up with the same span, the same subspace as a span. So what we should do, now that we think we have a good definition for linear dependence and independence, we should come back to that question and check. If we have a linearly independent collection of vectors, do we get the same span if we throw one of those vectors out? And conversely, if we have a linearly dependent collection of vectors, is it safe to throw away one of the vectors and still end up with the same span? So let's check both of those. So first we'll look at linear independence. So suppose we have a collection of vectors that's linearly independent, and let's throw away one of the vectors. So here we're going to say it's the last one. And let's compare the two spans that we get. The span that we get before we throw away the last one and the span we get after we throw away the last one. So the question is, have we changed the span by throwing away the last one? Well, clearly this second one is contained in the first, right? Every span, every v1 through vk minus 1, these are all contained in the collection from v1 up to vk. So the span of up to v sub k minus 1, this span is clearly contained in the span of all of the v's, just because with all of the v's you have just these, you have these few, but then some extras, right? So the question is, does having this extra vector v sub k give us a bigger subspace for this span? So this containment we know for sure, that one's pretty clear. The only question is, what about the other containment? Is it true that every vector in the span of v1 through vk is in the span of v1 through vk minus 1, right? And since these vectors are linearly independent, we are hoping that the answer is no, right? Our goal for linear independence was that when vectors are linearly independent, there aren't any redundancies when you take the span. So our hope is that the answer to this question is no. So let's check. So let's suppose that the answer is yes. Right, we're hoping that this isn't the case. So what we're going to do is just kind of assume, on the contrary, that the answer is yes instead of no, and derive a contradiction. If assuming that this span is equal to that span gives us a contradiction, then that means that this supposition is incorrect, which means that it's not contained, which is what we want. So if the span of all of the v's is contained in the span of the v's just up to k minus 1, that means v sub k would actually be in the span of v1 through v sub k minus 1, right? V sub k is definitely in this span. But how can v sub k be in the span of the v's? That would mean that v sub k is a linear combination of all of the other v's. So I guess up through a sub k minus 1, v sub k minus 1. But that means that the vector 0 is equal to a sub 1 v sub 1 up through a sub k minus 1 v sub k minus 1 minus v sub k. But look, this is a non-trivial linear dependence relationship, right? And it's non-trivial because the coefficient on this v isn't 0, right? So if we have a non-trivial linear dependence relationship, that means that v1 through vk are linearly dependent. But that's not true. We know that that's not true because at the very beginning we assumed that this was not the case. So this is wrong, right? This is false. So this is a contradiction. And that means that this supposition we made up here was false. So in fact, this shows that the span of v1 up through vk is not contained in the span of v1 up through vk minus 1, right? So in other words, these are not the same subspace. So this is good. This is what we wanted, right? If we have a linearly independent set, you need every one of those vectors to get the same span, right? If you leave out any one of them, that changes the subspace that you get as the span. Good, so that's one of the two things we wanted to check. Let's check the other one. So the other thing we wanted to check is that if we have a linearly dependent set, then it's possible to throw away one of the redundant vectors. So just for sake of argument, let's say that it's the last one that is linearly dependent on the first k minus 1 of them. So just like last time, this containment is clear. So now we just need to show the other containment. All right, well, v sub k is a linear combination of v1 through v sub k minus 1. So that means that we can write bk as a1 v1 plus ... up through a sub k minus 1 v sub k minus 1, right? Okay, so take any linear combination, say b1 v1 plus ... up through bk vk. So this is an element of the span of v1 up through vk, right? Every element in this span is a linear combination of v1 through vk. What we're hoping is that this vector will turn out to be in the span of v1 through v sub k minus 1. That will demonstrate this containment. We will have shown every vector in here is also in there. All right, so how could we do that? Well, to do that, we need to show that this combination of the v's is actually a linear combination of v1 only up through v sub k minus 1. So how could we do that? Well, let's write down all of these vectors. So b1 v1 plus ... up through bk minus 1 v sub k minus 1 plus the last one, so bk vk. So what we want to do is do some algebra so that this term disappears, and we only have terms for v1 through v sub k minus 1. But look, we know that v sub k is this linear combination of the other v's. So we can write b sub 1 v sub 1 plus ... up through b sub k minus 1 v sub k minus 1 plus, and now this last term we can replace with a sub 1 v sub 1 plus ... plus a sub k minus 1 v sub k minus 1. And now we can essentially combine like terms. So this is b1 plus a1 times v1 plus ... up through b sub k plus b sub k minus 1 plus a sub k minus 1 times v sub k minus 1. So this linear combination of all of the v's is actually a linear combination just of v1 up through v sub k minus 1. And of course this is in the span of v1 up through vk minus 1. All right. And of course, this is exactly what we wanted to show. This shows that every vector in the span of all of the v's is actually also in the span of just v1 through vk. So that shows this containment, and that means that these two spans are actually equal. So what we've shown here is if we have a linearly dependent set, you can throw away one of the redundant vectors without changing the subspace that you get as a result of span. Together with our last result, that if you have linearly independent sets, if you have a linearly independent set, you can't throw away one of any of the vectors. this shows that our definition of linear dependence and independence really does capture exactly what we were trying to capture in this phenomenon of vectors sometimes being redundant when we take span. So linear independence means you need every vector to get the same span, and linear dependence means you can throw away one of the vectors without changing the span.